My name is Sydney Evans, and I am the integration engineer.
My name is Ben Carnachelli, and I'm the CAD engineer.
My name is Zach Klaus, and I'm the test engineer.
My name is Thomas Gira, and I'm the manufacturing engineer.
My name is Wesley Schumacher, and I'm the systems engineer.
And I'm Bridget Kane, the project manager. Now let's take a closer look at our design.
The intention behind this project was to replicate the natural flight motion of a bird. This involves both the rotational motion around the shoulder joint as well as the translational motion of the wings flopping up and down.
After researching a few different ways to create this motion, we created a design which uses linkages and cant motion in order to create the flapping motion that we wanted. So, since we had no real experience making realistic aesthetics, we also decided to implement the motion onto an origami-style crane. This allowed us to still model the motion without having to design a lot of aesthetic parts, since that was not our focus. Here is a completed video of our design. Very early on in the design process, we created this prototype which shows the flapping motion, which we would later implement into our final design.
This is our initial CAD design. We use this CAD design to just get our minds around what we want to do and what we're looking for. As you can see in this design, we have the gears parallel to the wing linkages. The wings are doing a motion similar to kind of what we're looking for. Two reasons why we did not go for this design in the end was the tolerancing of the gears and placement is very difficult to get the mesh right and the manufacturing of that. And the wings do an up and down motion, but we wanted a kind of a more complex motion where the wings are doing up and down and rotational motion.
So once we had a prototype down, we could start doing a CAD analysis to make sure we got the motion right. So for this one, it's just basic shapes so that we could figure out the motion how we wanted it to and get the sizes right. So in the end, all of the joints ended up being a little bit different, and the base plate did as well, but this kind of made sure that our motion was how we wanted it to be. So once we had the motion study working out, we created this final CAD model to make sure all the parts that we were going to use were going to be final. So in this model, all of the green parts are outsourced parts, so they're bearings, clevis joints, and motors, and the red and blue parts are parts that we were going to make. The yellow ones are just a C-channel that we made ourselves, and the blue wings are laser cut. This made sure that our model would move how we wanted it to, as we got everything integrated, and some things changed in the end, but this was mostly how it ended up.
Due to unforeseen circumstances in our manufacturing process, our group decided to change some of our methods of production throughout the project. The clevises we had ordered were too small for what we intended them, and because of that we had to change both the push rod here and here. Because this rod was laser cut, we were able to quickly change the design and make new parts. The threaded rod, however, was more difficult to change and took longer. We also elected to laser cut the majority of our frame components. The base, body, and wings were all laser cut out of acrylic and allowed for rapid prototyping. This, however, had some issues involving our clamps and rivets. Rivets here holding brackets caused the material to break at certain points, which wouldn't have happened with the metal fabrication process.
Here we'll show a little bit of extra film about how we manufactured some of our parts.
During the design of this, two components were identified as components of concern for failure. The lower pushrod and this clevis. This clevis was commercially supplied and the lower pushrod was supposed to be made of aluminum. The other parts were not considered to be parts of failure because they either didn't bear as much load, take as much stress, or were significantly overbuilt. For example, the main axle is steel, whereas these parts are plastic and aluminum. When we analyzed the lower pushrod, it was treated as a member in compression in an alternating load, and this element right here was deemed to be the part most likely to fail because it's got a neck down, so we're going to have a stress concentration with fatigue loading. It was originally planned to be aluminum, so aluminum has a yield strength in the hundreds of megapascals. The most stress that this is anticipated to take is simply the weight of the wing to lift and lower it. That winds up yielding a stress in the order of kilopascals, in this case roughly 20 kilopascals maximum. So, as might be expected, the difference of 3 orders of magnitude of strength to stress yielded a safety factor in the hundreds. The second part that we were concerned of is this clevis, which is commercially supplied and made of plastic. So these are the commercially available drawings with their dimensions. This part right here, which corresponds to that right there, is the area of most concern because the load is all supplied to a pin right here. So this has to deal with both moment and shear. But once again, the forces at play are less than 5 newtons at most. So this part wound up not having any concerns with failure under fatigue loading. It also has a safety factor in the hundreds. However, while we were manufacturing these parts, there were some supply issues. The clevis was ordered in the wrong side, and this lower pushrod wound up having to be made out of acrylic. We reran the calculations for acrylic, but acrylic has a yield strength in the 60s of megapascals, and once again the stresses on this are in the kilopascals, so there's no anticipated failure there. The smaller clevis reduces the moment because there's less distance right here, so that reduces the stresses on it, and the stresses were still not a concern.
All in all, we feel that our design really met all of the project requirements. After a couple of design reviews with Greg Potts, we felt sure that we were ready to begin the manufacturing process. However, once we started manufacturing, we ran into significant issues with supply. These issues could have really hindered our team's success, but we remained determined to complete our project on our own. One practical thing that we learned was to pay close attention to tolerancing. Tolerancing issues were not a very big concern with our initial design, but when we started creating parts on our own and laser cutting instead of having them milled, etc., there were some issues that we did not account for. All in all, our biggest takeaway about tolerancing is that we need to make sure our parts fit together and that they stay together. Our biggest takeaway overall, however, was about flexibility and adaptability. These two components were really the biggest reason for our success and could have been the biggest reason for our failure. In the face of significant manufacturing backups, we took our project into our own hands and actually withdrew our fabrication request from the Idea Forge. Because of our team's skill, we were able to manufacture all the parts on our own and complete our project in time.